which is essentially a comparison of blood flow properties using computational fluid dynamics. So we have two endographs and two excluded have shared characteristics. They have also some differences. You know them better than me, but I think we can mark some. They are both modular bifurcated stent graft systems with nylon stents and wires, but Endurance is from high density polyester fabric and excluded from expanded PTFE. So an interesting thing here is that the flow divider of both endografts is positioned high in the aneurysm, so Endurance and excluded produce similar lumen morphologies after surgery. But what can we tell about blood flow? Is it similar as well? And how does blood flow adapt to the endograft? And we must not forget that the essence of endovascular repair is the restoration of blood flow. So in this way, we will get a deeper insight, and we will also explore the margins of endograft design improvements, but putting now blood flow at the center. So the two endografts have some different material. They generate a lumen morphology, they induce blood flow, and there we intervene and compare the hemodynamic properties using computational fluid dynamics. And someone might ask me, why not just use the Poiseuille's flow? A brief reminder, Poiseuille's flow contemplates the effect of diameter on pressure and velocity. So we have a bigger diameter, we get a lower velocity and higher pressure, and the reverse effect for smaller diameters. And Poiseuille's flow is in one-dimensional equations and derives after multiple simplifications. So we believe that this might not permit a detailed description of the flow patterns and properties, like in complex geometries like the one we work, the piston-based geometries. So the researchers have turned to more comprehensive equations, like the system of partial differential equations, Navier-Stokes. I marked them there in the bottom. Here I have for you screenshots of Mimic software. I want to say special thanks to Materialize for the free trial license. And in the axial view, we are marking the area of interest, and these parallel two-dimensional images are transformed in a 3D model. The models include only the lumen between the renal arteries and the iliac bifurcation, and smaller arteries like the lumbar or inferior mesenteric were not taken into account due to lack of information about the blood outflow and probably the minor effect on the central hemodynamics. And we also need to build a mesh and apply some boundary conditions on our models. Our meshes were composed of tetrahedral elements from a range to 500,000, 1,000,000, and 300,000. We didn't have patient-based boundary conditions, which is a limitation of the study. Patient-based boundary conditions, you can find such conditions from ultrasonography data, for instance. But our conditions derive from the literature, and specifically we put physiologic pulse pressure at the inlet, no slip boundary condition at the surface, which is a type of rigid wall assumption, and the time-dependent velocity waveforms at the outlets. The simulations are performed in a powerful Dell server owned by the Laboratory for Vascular Simulations. Here in the left panel I have the streamlines. In the right panel I have the helical structures, and at the center I have a zoom at the bifurcation combining streamlines and helical structures. And here you can see, prior to bifurcation, for both Endurance and excluder, we have some helical structures developing, which is in contrast to what we said earlier about Nellis. And the identification of the vortices is based on the L2 method. The L2 method is about, it finds a local minimal pressure, and around which this local minimum pressure, we have a development of the vertical structures. And if you see the bondage of helical structures and streamlines in rest circulation zones, confirms the usefulness of this methodology. Again, some charts. The interesting thing here is that all comparisons between the hemodynamic properties between Endurance and excluder were statistically significant. This means that although they produce similar morphologies after the surgery, they produce different blood flow. And specifically, we have increased pressure drop both in abdominal aorta and iliacs compared to Endurance excluder. We have lower Gaussian stress for Endurance in both control regions, and we have higher max velocity again in both regions for excluder this time. And Mirifield list was higher for excluder versus endurance at the iliac control region. So you might agree that when we want to compare, this comparison must take place in control regions that occupy the same length. So the abdominal aorta and iliac control regions that I have been discussing by now were designed to make the comparison between post-operative, perioperative, and normal models plausible. Exclusively for post-operative models, we can define additional measurement zones, such that ones that separate the graft main body and limbs. So, based on a post-operative model, we went at the level of the flow divider here, and we go up 3 cm and 4 cm up, and 3 cm up and 4 cm down, and we define the cross sections, and then the graft main body control region and the limbs control region. So in these zones, as I said earlier, when we make comparisons, we want equal control regions. But off the record, the results with these control regions keep the same tendency with the previous results. And specifically, again, pressure drop is higher both in the main body and the limbs for excluder. We have less, again, maximal shear stress in the main body and limbs for endurance. We have greater velocity for excluder in both control regions. But now in the main body, we have great mean helicity for endurance in the main body control region, and for excluder in the limbs control region. So again, the conclusions. Most comparisons revealed statistical significant variation. Blood flow is different, although that both endografts induce similar lumen morphologies. Pressure drop and velocity measurements are in favor of excluder. Endurance keeps the shear stresses in low levels both in the abdominal and the iliac part. Helical flow is more intense in the limbs of excluder and the main body of endurance. And some ideas for the future. Numerical studies can clarify the effect of endograft design on blood flow and offer optimization ideas. And the flexibility of simulations permits the application of could permit the application of pilot endografts in virtual patients prior to mass production. This might be interesting. Thank you very much for your attention.